Hey guys, welcome to part two of the chapter two lecture, where we're starting to talk about atoms and elements and the periodic table. And so we finished up part one on this slide, talking about multiple ways to distinguish elements from each other. And so we're just going to walk through a little bit on the periodic table. Some of the things that are going to be very important, at least on this aspect of the periodic table, and then we'll start adding a little bit more to it, especially when we talk about atomic weights, atomic masses. And so one of the easiest ways to distinguish one element from another is known as the atomic number, or Z. This is the top number. It's either found on the top middle or maybe on the top right or the top left on some periodic tables. Each periodic table is different. The atomic number is the number of protons that is in a element, or that is in that it's in an element. Now, one of the things that we're going to talk about when we talk about ions is that we're going to change the number of electrons. When we talk about isotopes, we're going to change the number of neutrons. One of the things that we're not going to talk about changing is the number of protons. When we start changing the number of protons, we start changing the elements. And so if we look at the periodic table here, let's say we look at carbon. Carbon's atomic number is 6. Carbon has 6 protons. Now let's say we add a proton to carbon, so now we have 7. We no longer have carbon, but we have nitrogen. And so one of the things that we need to do is we need to keep aware of, or we need to be aware of those atomic numbers. That will be very important in the next couple slides. The chemical symbol is another way that we can distinguish one element from another. And this is usually a 1 or a 2-letter abbreviation that we give to the element. And usually it's below the atomic number, so H for hydrogen, He for helium. The reason why some of them do not make any sense, like Fe for iron, you have Mn for manganese, but Fe for iron, some of those Au for gold, those weird ones that, like, why would iron? There's no Fe in iron. That actually comes from the Latin term ferrous, for iron. And so they took the first 2 letters of that. And so that's why some of them are a little different. One of the things you will not have to do in this class is memorize the periodic table. You will not have to memorize it. You'll be given it. Now, with that being said, we're going to commonly see some elements being used, things like carbon, oxygen, hydrogen, nitrogen, a little bit of fluorine, boron, some of those, lithium, sodium, some of those things. Now we're going to use enough to where you'll just naturally, again, memorize it with the practice that we use. You should be familiar, though, with some of the names, the more common names, because we are in chapter 3 going to talk about how to name compounds, name molecules. And so you will have to be familiar at least with a few of the things here on the periodic table. But again, you do not have to memorize it. So the same elements can vary, quote unquote, from one another, right? So we talked about carbon. Carbon has 6 protons. For an element to be carbon, it has to have 6 protons. It can't have any more, it can't have any less. But what happens is we can start varying, if you will, the carbon molecule or the carbon atoms, to where we could have a carbon with, let's say, 6 protons and 6 neutrons. We know that as carbon-12. Most abundant isotope, the most abundant type of carbon in the world. You can have carbon with 6 protons and, let's say, 8 neutrons. That's carbon-14. Carbon-14 is what we use to date things, to see how old something is. Carbon-14 and carbon-12 are examples of isotopes. It's the same element with different number, it should say, of neutrons. Sorry for the typo. Of neutrons leading to a different mass number. Because again, if it's a different number of protons, it's a different element. And so it should say neutrons. Protons and neutrons are around 1 atomic mass unit. And so that's why we can say, carbon-12 versus carbon-14. I'll show you guys how to calculate isotopes and how we can use a special way to write them to tell us how many neutrons there are. Isotopes occur at differing natural abundances. Some are more abundant than others. And what we'll do is we'll use these, and we'll talk about these a little bit when we talk about atomic mass, the atomic mass of these elements, and why they're not exactly round whole numbers. Now, there are two two elements that have only one isotope, beryllium and aluminum, right? There's only one there, whereas others have multiple different types of isotopes. The example that we're going to use here is we're going to look at neon, right? So how do we name elements and isotopes, right? How do we distinguish one isotope from another? Well, there's two different ways we can do it. We're going to start with the bottom way. The bottom way, as you can see in the table, is the first way depicted, and that's where you do the chemical symbol or name. So in this case, it's neon. So Ne, or that you could spell out neon, and then the mass number, neon 20, neon 21, neon 22. I'll show you an example on the board on how to do this with carbon, right? Another example on carbon. The other way to do this, and the way that you should be familiar with, is the top way, where you have the mass number on top. So in this case, let's look at neon 20. You would have 20, and then you would have Ne, the chemical symbol, out to the right of that. And then below the atomic mass, or the mass number, you would have the atomic number, which would be 10 in the case of neon. Now notice, if we look at all three examples of neon, the atomic number does not change. Why is that? You're right, because if we were to change the number of protons, if we were to change the atomic number, we would change the element. Now, let's look to see what this looks like with carbon. All right, so we come to the board, and so we talked about carbon 12. And so there's two ways we can do carbon 12. There's that way, where we just write 12 carbon, or even that way. Or, if you remember, we do atomic weight or mass, and then the abbreviation or the chemical symbol, and then the atomic number. Now, we also said there was carbon 14. So I'm going to draw carbon 14 to the right of the carbon 12. Here's the question. How many neutrons are in carbon 12, and how many neutrons are in carbon 14? Well, there's an easy way to tell how we can do the number of neutrons in both of these examples. And here's why this is very powerful of a way to write an isotope. Because if we just were to take the atomic mass, or the atomic weight, minus the atomic number, we are given with the number of neutrons. Right? And so if I were to say on an exam, let's say, how many neutrons are in neon 20, right? You would put 20, Ne for neon. You would put the atomic number for neon, which is 10. And so then what you do is 20 minus 10 would equal 10 neutrons. And that would be the number of neutrons in neon 20. And so, so that is the way. Switch back to the other camera. Let's go and share the screen. And so that's the way that we can depict isotopes. And it's very important, right? Because like we said, the isotopes are abundant in nature at a different amount. And so we need to know how many neutrons are in these. Another thing that we're going to talk about is ions. One of the ways that we're going to see in the next chapter, chapter 3, that two elements can combine is through an ionic bond. And so to make an ionic bond, you need ions. When an element loses or gains an electron, it is called an ion. Electrons are gained and lost in reactions. We're going to talk about electrons in reactions later. If a proton or neutron is lost in a reaction, that is known as a radioactive reaction. You guys will cover that if you stay on to Gen Chem 2. You'll cover that in Gen Chem 2. Let's talk about the different types of ions. There's two different types of ions. There's a negatively charged ion and a positively charged ion. Each ion has a special quote-unquote name to it. An anion is a negatively charged ion. Now, how can we remember this? Well, we can remember this by the little picture, that onions, right? Onions are bad. They make you cry. An anion, very similar to onion, is a negatively charged ion, right? Negative means bad. Whereas a cation is a positively charged. Cats are good. At least to some people, cats are good. But cats are good. And so it's a positively charged ion. So cats are good, positive, onions are bad, negative. That's the way we can remember uh, cations and anions. Now let's look at the periodic table that's up here on the slide and see if we can see a few patterns, because there is a few patterns that we can start seeing. We haven't talked about. In the next slide, we're going to talk about how we can organize the periodic table in a variety of different ways. But here, what we're going to see is we're going to start seeing the patterns that are found in the periodic table. On the far right, as I'm looking at it on the far right, you see a bunch of anions. Things like oxygen, fluorine, chlorine, bromine, sulfur. We're not going to exactly talk about why they have the charges they do now. We'll introduce that a little bit into chapter 3. But just notice that these are all what's known as non-metals. These are all gases, right? Oxygen is a gas. Phosphorus isn't necessarily a gas, but it's a non-metal. Bromine is a gas. Chlorine is a gas. Iodine is a gas. All those gases, all those non-metals are negative. They're anions. They form an anion. To form an anion, they need to accept an electron. So the way I explain this is that the nonmetals are the most unchristian elements in the periodic table because all they do is take. They take those electrons, they steal them, they take them, and they become a negatively charged anion. Now, if we look at on the left side of the periodic table, we see a bunch of metals. Lithium, sodium, magnesium, potassium, calcium, right? Those are all metals. And one thing we notice is a lot of those metals are cations, right? Metals like to give up their electrons. Non-metals like to take electrons. So the metals are the most Christian elements of the periodic table, and they're going to just give up those electrons pretty easily, at least one or two of them. And so this is just a trend that we need to start thinking about, putting it in our mind, that cations are usually metals, anions are usually non-metals. Since we're talking about metals and non-metals, these are the main ways that we divide the periodic table. Let's start with the main group elements and the transition elements. You'll notice on a periodic table that you have some peaks, right? Columns 1 and 2, 3, 4, 5, 6, 7, 8. Those are peaks. Those are known as the main group elements. Everything between those peaks is known as a transition element, and transition elements are usually metals. They're usually metals. Some of them are radioactive, some of them aren't, but at least they're transition. We are going to be a little bit in those transitions. We're going to talk about the most common transition metals in this class. We can also divide the periodic table in the states of matter, if you will. We can divide it up into metals, non-metals, and metalloids. And so non-metals, we're familiar with metals, right? They're good conductors of heat or electricity, right? The copper wire that runs the electricity, the metal pan that we use to cook food with, those are good conductors of heat. That's why we can do it. They're very they can be pounded into flat sheets, drawn into wires. They're shiny. They lose their electrons pretty easily. Non-metals, some are solid at room temperatures, but usually they're gases. They're poor conductors, right? They tend to gain an electron. And then the metalloids, several are superconductors. And what I mean by superconductors is their conductivity is dependent on temperature. Usually the colder they get, the better they are at conducting both electricity and other things. Those are the things that we usually see in our computers. And so just on the broad scale, this is a way that we can start dividing the periodic table of elements. We can further divide the periodic table of elements into what's known as families or groups. Usually these things are seen in a column. Row number 7 is halogens. These are very highly reactive gases. You have fluorine, chlorine, bromine, iodine, right? Chlorine and iodine are used as disinfectants because they are so reactive. In pools and bleach uses chlorine. Chlorine gas is very toxic to a human. Then you have alkali metals, column number 1, group number 1. These are very highly reactive metals, lithium, sodium, potassium. If you ever seen, and I would recommend maybe going to YouTube and looking at these alkali metals and their reaction with water, it is quite impressive. I would recommend doing that. You have other columns. Column group number 8, you have neon, argon. These are known as noble gases, very highly unreactive gases, mostly unreactive gases. You get to the bottom, you can start reacting a little bit. And then you have the alkaline earth metal, group number 2. These are fairly reactive, things like calcium and magnesium. In the lab, we're going to see calcium and magnesium, at least calcium and other metals and copper, and the way that they react with other chemicals. And you guys will be able to do the experiments with this. Now, I went through that pretty quickly. You should be familiar with the different groups. We'll come back to them later in the semester, so I would recommend learning them now. The alkali earth, the alkali metals or alkaline, alkali, both are the same. So group 1s, group 2s, group 7s, the halogens, as well as group 8, the noble gases. And so I'm going to leave you guys with this. For this part, we're going to do chapter 2 in 3 parts because we will have a good a small amount of math at the end. But here's what I want you guys to do. I want you guys to start thinking about. So I took off when we started talking about that periodic table. There was one number missing, and that's the atomic mass of the element. It's the calculated average mass of the sum of all natural isotopes. You know, it's usually placed under the elemental symbol, and you notice that it's not a whole number, and that's because it's a sum of all the natural occurring isotopes. And so how do you calculate the atomic mass? You have the fraction of isotope n. So let's say there's 75%. So you'd have 0.75 times whatever mass that is. Let's talk about carbon. So let's say 75% is carbon 12. You would have 0.75 times 12 plus 0.25 times 14. So you would do that, and then you would divide it by 2, right? And that's the atomic mass that goes onto the periodic table. And so we're gonna and so now what we're gonna do is, now we know the atomic masses of things because it's on our periodic table. We are going to now start to do some calculations using the mass, so we can calculate how much of a sample we have. But that's going to be in part 3. So hopefully you guys have enjoyed part 2. Part 1 introduced atoms and stuff. We're now starting to build on that foundation in the periodic table, and then we're going to build on this foundation and do some calculations with regards to how much of something we have.